Thank you very much. Appreciate the organizers including me in this workshop. The next lecture for the next 90 minutes will seem somewhat out of place in that there will be no dynamics or anything like that. And the purpose of the lecture is really just to develop the basic components that you would need to write down a dynamic model. This work is in no sense as familiar as Harold Zurcher. Nobody's had anything named after it except Vickery. So almost all of the material in this lecture is from a book or a little lecture I wrote with Matt Gentry, Tim Hubbard, and Dennis Nekopolov. And so it's in the readings. If you don't have any background in auctions, then this is a trade book I wrote with Tim Hubbard. You could probably read it in an hour. We were constrained to have 6 pictures and no more than 2 equations. So there are a lot of words. I wrote a book with Han Hong a long time ago, and in part for that book, to implement what was in it, I developed this, well, actually, my former student, Ryan Haley, developed a suite of MATLAB code that you can use. And then if you don't know how to compute, which seems unlikely in this crowd, I have a book for people with no experience with Konstantin Golev. So that's kind of the background. I don't have anything like Fedor or John in the terms of web pages. I'm pretty old school. You'll see that in the next set of slides that are, well, from another century, quite literally. So perhaps the biggest success story in economics in the 20th century, certainly the last half, was this systematic study of incomplete information in economic environments. And, you know, the kind of the polar extremes are moral hazard, insurance, and then adverse selection in auctions. And that developed in tandem with game theory after the Second World War. An important research program was the formulation of these problems as mechanism design problems or market design problems. Theoretical models of incomplete information are particularly compelling to me, at least, or econometricians, in that they provide a richer explanation of observed heterogeneity in data than ones that rely on measurement error or productivity shocks. I'm not saying that measurement error and productivity shocks aren't important, but in auctions, there is no measurement error in the data, right? So it's hard to generate an empirical specification, and typically in the models, there are no productivity shocks either. So they're models of exactly what, you know, unobserved heterogeneity. And they're interesting because when individual agents use this private information strategically, you can get phenomena that are quite different than what you would expect in certain models, certainty models. And then they've had as you've seen, a big impact in industrial organization. So the canonical problem to all economists is, how do you sell something? So you're a seller and you have an object, and you can do it in a number of different ways. What makes the problem difficult is that you may know what it's worth to you, but you have very little idea about what the potential buyers have about it. And you would like to try to construct a mechanism so you as the seller could get the most. But the existence of this asymmetric information makes that impossible. And so that was kind of the result that came out of Satterthwaite and Williams. It said that, you know, you could never get to the Pareto combination in bargaining, right? We always talk about the place inside the Edgeworth lens where suddenly we come to an efficient bargain, and that's not possible with asymmetric information. And if you've ever had an advisor from Chicago, that just used to enrage him for reasons I never understood. It was just a model. So one way to do it is you just announce a price, right? And I think folks think that that's the norm, but up until around the 18th century, this was not the norm, right? The fact that you would charge all customers the same price was more or less brought in by the Quakers in the 1700s in Philadelphia. Prior to that, if you wanted to buy something from a merchant, you went in there and you haggled. So you bargained. So the most common way of selling things would be bargaining, but we know that that has, some transactions costs. More importantly, in bargaining, there's always this holdup problem. And what's very attractive to selling something at auction is that the fact that there's another party in addition to the one you were originally bargaining really gives you a lot of power. You can't totally exploit the rents of that power, but you can get some word. So, but you should understand it's not the only way to sell something. And a standard example I like to give about this is from a book by Henry Winchik, which was a biography of George Washington. And in it, George Washington is a fairly young man, and a friend of his dies. And like many upper class Virginians at the time, the man was land rich but cash poor. And so, and most of these Virginians lived way beyond their means. And so when they died, they had lots of debts. And the standard ways to dispose of this debt was to sell, livestock, which could include people. And Washington chose not to do that. And instead, he held a raffle. For some of you, a raffle is a pretty rare word in English. It's essentially you give people, they buy tickets from you, and then you pull tickets out, and the one ticket you pull out wins the raffle. So it's like a lottery. And it turned out that this raffle made huge amounts of money for Washington's friend. And the reason was in Virginia at the time, distance was tyrant, right? So if you needed to go from Madison's house to Jefferson's house, that could take you a day. Whereas today, you would drive maybe 30 minutes in your car. And so you just weren't going, you weren't loading up one day to go, even if you were aware of the auction. That was the other thing, that distance made it impossible to advertise really well. As I mentioned, most Virginians were cash poor, but they could always afford a little flutter on something. And so the point is that with a raffle, you might get much different participation rates than you would with an auction. And even though the price was small, the numbers that participated was large, and you could make more money. So the basic idea is that there's a set of things you can choose from to sell something, and an auction happens to be one. And however much I like them, they are very unusual, right? They are formal markets, and economists like them because they're formal mechanisms about how prices obtained, but they're very rarely used because they're extremely expensive to conduct, right? Most of you don't participate in a market either, right? Virtually all labor is not in a market. Somebody quotes a price and then you work there. But where that price came from, in the background, we think that there's a market, and then I guess there's something like it. But think about if you're in a firm and you go from one level to another, there are no markets. So the bulk of transactions are not done by auction because they're expensive. The ones that are done are for things that are really important, like treasury bills or things like that. Why? Because the price of those bills has implications for how all sorts of other things are priced, and you want to get that initial price right. Why are writing down formal models of auctions interesting? Well, you can use the primitives from them to do market design, mechanism design. And in that theory, they're kind of like two agents, principals, sellers at auctions, and agents, potential buyers. And the incentives of these two parties are not aligned. You know, the seller wants to get the most and the buyers want to pay the least. And so in the theory of mechanism design, you get to choose the rules, and you can choose those rules however you like. You know, maximize some objective. Could be seller's revenue, could be surplus to the pair. It's up to you. In some sense, it's a little hard to think of surplus to the pair when there's kind of a fixed pie, but you get the idea. The first person to think about this in any serious way was Milton Friedman, and he went back to looking at how, you know, treasury bills were sold in the U.S. And he thought that was important because the prices in those markets fed through everything. And at the time, I think they were using pay your bid. And he proposed, you know, an alternative. William Victory responded to that with something that was very clever, but almost irrelevant. And what do I mean by that? Well, treasury bills are an example of something that is a common value object. And the models that Vickery employed is a private value, right? So they're really models of different phenomena. In any case, Vickery, you know, formally demonstrated that a wide class of auctions provided revenue equivalence. And so Milton Friedman's question was in some sense by the by, but you know, if you were to go to a common value paradigm, you'll find that this result does not hold. Right? So it holds for a specific kind of environment. Auctions are obviously very important because they've been around for a long time. So if you believe in anything evolutionary, you know, this is a pretty decent mechanism. The main defining environment is this existence of incomplete information, this asymmetry of information between the seller and the potential buyers. And in many situations, there'll be multiple places where that can enter. And then you have to decide what is the most important one. As it stands today, we don't know how to deal with many versions. So you got to figure out what's the first order important one. And that often in any application involves you literally working in that industry or something. It's not going to be something you can think about. You'll have to experience it. As I mentioned, the buyers have no incentive to tell the seller or any of their competitors anything about their valuations. And the auction plays an important allocative role by inducing the potential buyers to reveal that private information. There are kind of two basic rules for an auction. One is allocating the good for sale efficiently. And that's typically, if that's your object, you want to use something like a private value paradigm. The other is price discovery, as in the case of, say, the treasury bills. And those are typically common value paradigms. There is a paradigm that's in between, and it's called the affiliated values paradigm. One of the things to note is economists are unusually vague about where these valuations or come from, right? I mean, I say that in contrast to, say, you know, the first 5 weeks of a micro theory course in graduate school, where they go over all sorts of axioms until your head hurts, right? Here, there's just a little urn, and you take draws out of it. It requires no thought. And there, for economists, I find this pretty odd. There's no budget constraint, and there's no substitution. So this is a really peculiar world from an economist's perspective. Perhaps not as peculiar as the Keynesian model, where there are no price adjustments, but pretty peculiar nevertheless. So you've got this group of folks. I identify them by big N, and they're potential buyers. and they get this draw from this earn, big F, that has a PDF, little f. Vickery did all his work in the uniform example, and that seems somewhat limiting, but in this world, you can always transform things. In fact, lots of people do it in terms of types, that types map the values, but the point is that this V is the private information of a potential buyer, and we call this a symmetric independent private values model because they all come from the same earn. That's the symmetry, ex ante symmetry. And this, you can think of this private value, this type, as the marginal utility they have for a particular good or object. And if there's more than one unit of the good, then you take two draws, they're independent. When you start to get almost like a demand curve, right? The highest valuation, then the next. If you have 30 goods, you take an independent draw and you get this little approximation to a demand schedule. So if you have n folks, you can order their evaluations from smallest to largest, and you'll notice there's been a slight change in notation. I use little n for the index, big N for the top end, and then I use this notation 1:n in the subscript 2:n, n:(n) to denote the order statistics. Here, imagine what this would look like when n was 9, where you get this little step function of demand, and you can kind of see, if there was one object for sale, well, then it would, the price that cleared it would be someplace between the second and the first order statistics. If there was 5 units for sale or 6 units for sale, it'd be somewhere between those adjacent order statistics. In the world of imagine if there's just 1 unit for sale, the second order statistic has a special meaning to us. It's the value of the object in its next best alternative. In other words, the opportunity cost. And so that's why folks fixate on this second price auction, because the price at that auction, or the average price, if it's the average of the second order statistic, represents something that economists hold dear. So one of the things you would like to know is, this is a sample analog. This is the sample demand curve. What does the population look like? Well, it's a survivor function. What you want to look at is what proportion of the sample would buy if the price was below at some level. Let's suppose the price is V. Well, it's the sample in the right tail of the distribution. Everybody in the left would not buy. And so it looks like that. And that's the object that you want to estimate. That's what you want to know. And you don't get to see it. At best, you might get something like this, but even that's optimistic. So what often you get to see are some bids. The bids are monotonic functions of the valuations. If there's a reserve price or something, you only get to see a selected sample, and you would still like to know under what conditions you could recover an estimate of this survivor function. This is the demand function. And from this demand function, if you could recover, in some sense, the monopoly price, and that would be the reserve price. Right. So this object here is central to all sorts of things. Even if you were not going to have an auction and you wanted to choose the take it or leave it price, it's going to be derived from this object. So if you were going to sell non-fungible tokens on some crypto exchange, you need to know this object in order to price them, if you're not going to use an auction. So how does this relate to the whole population? Well, you've got n potential buyers. They want 1 unit. So n times this is their demand curve, and it looks something like that, the expected demand curve. And you get some realizations. So imagine you did. Imagine you're in the best case world. Everybody's truthfully tells you their marginal utility. Well, then you could use a Kaplan-Meier type estimator from duration theory to fit what you have to approximate the demand system. You don't get to see those V's, right? Those V's are the private information of the buyers. And so the question then is, how do you get those folks to reveal that information? Well, sometimes they don't reveal any of certain auction formats don't allow you to see anything but that of the winner. Imagine a Dutch auction where the price falls. You only see the winner. So how are you going to recover that object from the winning prices? Similarly, at a first price seal bid auction, you may observe all of the bids of the participants, but not the non-participants. Why don't you see the participants? Well, you have to have an idea of that. Anyway, the point is that different auction formats, open outcry, seal bid, and different pricing rules, pay your bid or second price, provide potential buyers with different incentives concerning how to bid. And that's then going to give rise to the quality of information you get to estimate this SOV, this survivor function. So under a pay your bid rule, a bidder's action determines what he pays should he win. Whereas under a second price rule, the action of his nearest rival determines the bid he pays. And so when your action determines your payoff, you're probably going to lie. And when the price you pay is determined by some independent neighbor, you're probably going to be pretty truthful. So what we know is that second price auctions, the bids are going to be much more truthful than they are at pay your bid auctions. So the main feature here is that in equilibrium, different functions map the private information of the potential bidders into their actions. So the things we're interested in are their types or their valuations, and we just get to see their actions. And there has to be some link, right? In general, you have this distribution G of B, and you can estimate it any way you like, non-parametrically, but the link to F of V is without some link, there's no way to link to recover, to reverse engineer F of V from G of B. So what to do? Well, I mean, in economics, there's typically three fundamental hypotheses that we invoke. The first one is that there is scarcity. So in the auction model, that's 1 unit for sale. The next is you have to have some sort of objective, because the hypothesis of optimization is going to give rise to some sort of behavior. In most of this literature, they focus on, the expected payoff. So the valuation minus what you bid. And then times something called your probability of winning. And so it's expected profit. Now, it turns out that those two hypotheses together are not sufficient to close the system. In Chicago, first year economics, right? Because markets are perfect, you can work off the first order conditions, but this is not an environment where markets are perfect. Your opponents have power. And so you have to close off this model with a concept of equilibrium, and that's what determines all of the action. And this is truly somewhat unfortunate because economists don't have very many notions of equilibrium, and the ones we do have impose stark restrictions on what we get to observe. So what are the four kind of auctions we're going to study? Well, there's going to be an oral auction, an open outcry, and it's going to have two varieties. One is it's an ascending price. We often call that an English auction, and when we model it, we call it a Japanese auction. I'll be a bit clearer about that later. And then there's another kind, a sealed bid kind, and those have two pricing rules: first price and sealed bid. What you can show is that in one of these environments, so when you have second price sealed bid or English auctions, it's a dominant strategy for you to reveal your type. That's an equilibrium. In the other two models, what you find is that you have to impose a darker concept, one known as Bayes-Nash. So let's start with the English auction. And one of the problems with these oral ascending price auctions is that reality gets in the way. And one way to shut down that is to take a position. And the position that Milgram and Weber took was to imagine that this is a thermometer or a clock, and it starts at some low price and it rises, and you, by holding up a card or by pressing a button, you affirm your willingness to pay that price. And so you can imagine sorting the valuations of the potential buyers from largest to smallest, and you know what their type was. Let's suppose the valuations are 5, 3, and 1, and the clock is rising. The third guy is going to drop out at 1. Second guy is going to drop out at 3, and the third guy is now the winner. And so he pays what the nearest guy was willing to pay. And that, as I mentioned, has this important meaning to us. And you can see, therefore, why economists are attracted to stuff like that. Second way to conduct an oral auction is to do what they do in, say, Aalsmeer or almost any place that sells fish, is they have a big clock. The clock has 100 little points around it. It starts at some extremely high price and it goes down. And then you get to stop the clock by pushing a button. And what's interesting about those is, even though they're both oral auctions, the equilibrium in this, what's often referred to as a Dutch auction, a descending price auction, is that you bid less than what it's worth for you. You shave your bid. And the amount you shave your bid depends on basically two things. One is how many competitors you face. And typically at a Dutch auction, that's easy to verify because you're all in the same room. And the other is the shape of that valuation distribution. If that valuation distribution is really compact, then you're not going to shave very much. If that is really wide, you're going to shave a lot. Talked about that. So what are the kind of the important things that people point to? In the symmetric independent private values model, there's no information release regardless of the type of auction. Right. So if you're in an English auction and you're seeing people drop out, that doesn't tell you anything about your valuation, because your valuation is an independent draw. Similarly, in the Dutch auction, when are you going to push the button? Well, given your valuation, I won't wander. I once had one of these when I was teaching MBAs, but they didn't have this. They had you on a cord, and I kept getting, like this. And I commented that even my ex-wife held me to a longer leash than this. And well, just say the dean was not happy for some reason. probably because they complained. So the point is that in this auction, if you have a valuation, you have the highest valuation, and so you're going to bid as if you do. You don't want to be fully revealing. You only want to, on average, bid what your nearest opponent would bid, namely the second highest valuation. And so you can already see where revenue equivalence is going to come in, is that in the Dutch auction, you're going to shave, but on average, just to get the second order statistic. But at the English auction, you're going to bid up to your valuation, which means you pay the second evaluation. So on average, they're going to be the same. What is going to be, however, different is because they're different functions of the information. They'll have different distributions and they'll have different moments. And I'll show you that in a picture later on. You can almost see the result. The second order statistic itself is going to have lots of variability. The first order statistic is going to be to a first approximation a fraction times the valuation, and so its variance will be much smaller. The Dutch auctions will be truncated, and the English won't. These matter to someone who's going to use an auction. If you're worried about variation, then you're not going to like this the one that provides you the prices, like second the opportunity cost prices. Okay. So here's what an English auction strategy looks like. It's the 45-degree line, and here's the Dutch auction. And you can do this for first price and Vickery auctions. And the Vickery will be the English, and the first price will be the Dutch. So they're really just two strategies, which makes life much simpler. So from a policymaker's perspective, even though these mechanisms yield the same revenue on average, is there any way to improve it? And there is. In fact, Meyerson, as well as Riley and Samuelson, showed that the optimal selling mechanism involves a reserve price that looks like this. And so now you can see why, when I was a graduate student, mechanism design was viewed somewhat unusually, because that most folks thought it was effectively sterile. Most of us don't know what that distribution of valuation is. And at the time, there was no idea of how you might reverse engineer anything you observed to get that estimate. If you impose the twin hypotheses of optimization and equilibrium, you can uniquely identify FV from G of B. And so the problem is effectively solved. And so one way to think about the structural econometrics of auction is it's an identification strategy. Sure, there's a lot of stuff that comes after it, but without that identification strategy, there would be no literature. For some bid functions, it's pretty simple, right? If you observe the distribution of bids at an English auction, you know the ones at you know what the distribution of valuations. Whether you can non-parametrically identify the distribution of valuations from a non-parametric from the Dutch auction is another. It was an unresolved question, which Gare, Perrine, and Vol resolved. Now, at this point, there's kind of a tension. You usually use auctions in cases where you don't have a lot of data, and non-parametrics by construction requires a lot of data. And so, you know, if you may often have to use parametric models to essentially dimension reduce the problem, much in the way you would use the lasso to regularize. And so one one kind of field of endeavor, at least among some folks, is to think of theory as a dimension reducing stuff, as a form of regularization. When you do that, you accept right up front, no closed eyes here, that you're going to get bias, right? So there's always going to be this tension. If you do non-parametrics in this world, you will get huge standard errors. They will tell you things like, oh yeah, the optimal reserve price is between minus infinity and plus infinity. And I already know it should be positive. So I don't need to do all that work to find that out. Yeah. So why are auctions, or why did I find them interesting about 40 years ago, is that the rules that govern them put very tight predictions on the data generating process, unlike in some other applications, right? And in fact, many of the models are written in things that you as an econometrician or as an empirical worker would like to see. And so I find that helpful. I think I went too far. Okay, so what is the value of this structural approach? Well, under certain conditions, the twin hypotheses of optimization and equilibrium allow you to identify the unobserved distribution of valuations. You can then, from that, reverse engineer, estimate it. But the really important thing is to conduct comparative institutional design to see if there are ways of improving on what exists. And sometimes there are, and sometimes there aren't. So, as I mentioned, auctions will give you a very tight mapping between the behavior of bidders and what it is you're trying to look at. If you think about what happens in, say, labor, first of all, the data are plagued often by measurement error. Maybe not the kind of measurement error you're used to thinking about, but you can think of a person trying to remember how many hours they worked last year. And, they're going to do something like say, well, I average about 40 a week and I work 40 weeks, so maybe 2,000, right? There's no measurement error in auctions. These are legal contracts. You could build in a model where there are shocks, but for most environments, they've already been revealed by the time they have an auction. So the main thing that is in there is unobserved heterogeneity. And these are going to be techniques to get at that. Okay. So when you introduce a binding reserve price, so you've actually calculated the optimal auction, there's kind of a little bit of a problem, is that this optimal auction introduces an inefficiency in the sense that some fraction of the time you're not going to sell the good, right? And you can actually calculate the probability of that. That's when all end bidders have a valuation less than the reserve price. Then it just goes unsold. You just burn it. And that simple example kind of highlights the tension between, revenue maximization on the part of the seller and allocative efficiency in general, right? And for some people, that's a hard concept to get over, but it's there. Am I going backwards?
Yeah. It's been going backwards for a while.
It's been going backwards for a while, and I haven't noticed. Have I been repeating slides? Because that would be really embarrassed.
You skip some of them that start going backwards.
No, we did this one. Okay. Okay. Good. Good. Okay. Okay, so I'm going to dwell on a particular example. I'm going to focus on an IPV model English auction clock model. And there's going to be, I want to show in some sense how you can get from this, the thing you want from the empirical distribution of bids from a cross section of auctions, how you might be able to get to an object that would be impervious to the Lucas critique. So I don't never know, how many of you don't know what the Lucas critique is? Put your hand up. Just one, two. So the Lucas three, there's a Lucas critique is this notion that you can't learn anything about policy from reduced form data analysis. So anytime you see someone run a regression and then try to, from that regression, predict what'll happen to tax policy, the natural question is, if you really want to annoy them, is to put up your hand and ask them about what the Lucas critique is. And invariably, if they did that, they won't know, and then, you know, it won't end nicely. But the basic point is, if in this world, you're literally changing institutions, right? You're going from, say, an English auction to a first price sealed bid auction for whatever reason. And that's going to have the notion that if you just looked at the average price at a bunch of English auctions and then try to make some prediction at what would happen at first price sealed bid auction, that has to seem at least odd to most of you by now. But you know, 40 years ago, it wasn't obvious. So the thing about this is that in the presence of a binding reserve price, which often exists, is you get endogenous participation. And the question then is, can you learn enough about that distribution from what you get to see to what you need to calculate the optimal reserve price? It must not be a big shock to any of you if I tell you, if you don't get to see a big chunk of the valuation space, because everyone who has bids below that doesn't show up, that you're never going to identify the bid distribution when there are reserve prices, right? The lower end of the distributions. People have different reactions to that. They say, well, it doesn't matter because we never know, we're never going to go there. I don't know, right? How do I know that the existing reserve prices aren't too high? So you're going to have to make a distributional assumption. I've always envied John's literature because no one ever gives him a hard time by invoking the type 1 extreme value distribution. Everybody just accepts that and bows to Mecca. In this industry, you know, if you don't non-parametrically identify your model, you're in a heap and helping a hurt. It's just going to go on for days.
Life's unfair.
Yeah, no, life's a bitch and then you die. Exactly. So the thing here is that if you have any sort of covariate heterogeneity, any sort of reserve price heterogeneity, any sort of heterogeneity in markets, such as the number of people participating in any given market, you are only ever going to get anywhere with parametric assumptions. And if that's unpalatable, you should just write another paper because life's short. So you have to embrace that. And if you don't want to, I don't mind, but you're not going to get anywhere in this industry non-parametrically because there's just too much observed heterogeneity. Now, so what'll a bid function looks like? Well, it's like this. The Bayes-Nash bid function looks like that. And you can see they're quite different. So what I want to study a bit now is how different transformations affect what you get to see, right? So the first one is an indicator, like how many folks, whether a person showed up or didn't. The second one is a monotonic continuous transformation. And the third one is an order statistic. And these are all things that you're going to encounter in this literature all the time. So what is going to happen? Well, think about, you've got a sequence of NVs, and now you're going to take a transformation of them. If V is greater than R, it's going to be a 1 and 0 otherwise. So we've taken a whole bunch of information that had a whole bunch of values that had lots of information, and we've kind of basically, made it Unix, because there's no information, just sign essentially. But those signs have structure. They're Bernoulli and they're IID. So when we add them up, we know what we got. The number of participants at an auction is a binomial, and you know what the probabilities are. And so those are going to be important in building the likelihood function of whether someone showed up or didn't show up. I'll call that M. Why? Because it's less than M most of the time. And what's really important is that all the theory is done in terms of N. Right? That has to be exogenous. M, on the other hand, is an endogenous variable. So when you see people regressing bids on the amount of realized competition, you know there's a problem. There's an endogeneity problem. They say things like, well, when M is larger, I get higher winning bids. Well, sure, more people participated, but also more people had large values. You can actually calculate what the PMF looks like, right? Here's uniform random variables when 5 folks in 0.2, you can get all sorts of nifty patterns. The next one is this monotonic transformation. I'm trying to build to what the distribution of bids looks like at a first price seal bid auction relative to, say, an English or a Victory auction. So we know that in any little interval, dV times FV, which I'm going to call A, the mass for the corresponding mapping has to be Fs times ds, right? And therefore, we know that the distribution of S is related to the distribution of V through 2 things. First, that dV/ds component, the Jacobian, and then this inverse mapping. So we can put the inverse map, and that the derivative of the inverse mapping is that there. So here's the picture. You're in this interval between V0 and V0 plus delta V, and there's the corresponding B. So when you have a value, the other thing to note that's somewhat different, if the V is distributed on V lower bar to V upper bar, let's suppose V lower bar is 0, and V upper bar is infinity, okay? The S upper bar is well inside it. Imagine that you have the highest valuation possible. Are you ever going to bid that valuation? No, never. You're going to bid, what is that S upper bar? S upper bar. It will be the expectation of the second order statistic distribution evaluated at the upper bar. You would never bid more than your opponent who has the highest value. So in other words, even though the support might go from 0 to infinity, the support of the bid will be very much smaller. And I'll show you how much smaller. Okay, so now we can calculate what the distribution of S looks like. Well, it's df ds, which is df of V sigma inverse, and we get down to here. So we have a mapping between the distribution of valuations and the distribution of bids. And it looks like this. So S upper bar depends not only on F of B, but on N. And if you have any covariates, it belongs on that. And why is that important? Well, this is a violation of one of the principal regularity conditions that is used to prove that maximum likelihood is consistent and asymptotically normal. And so that's going to change the game substantially. And if you want to really look at what that derivative looks like, well, that's what it is right there. So it's a bit of a mess. Okay. So by direct substitution, that's what the distribution looks like. And you know, that integral in the denominator and the calculation of that inverse function, it is what made this somewhat computationally arduous in the initial time. So how I spelt his name wrong, Quang Vuong. What was an amazing contribution by Gare, Perrine, and Vuong is that they provided a constructive way to calculate sigma inverse. So we know that this is true because that's the first order condition of the auction. We know that this is true by that picture. And we know this is true by the delta method. And so what you can do is if you manipulate these little creatures here, is you can show that V is equal to S plus big F of S over N minus 1 times little s, F of S. And why is that interesting? Well, it's in terms of things you observe, right? You observe the bids. So you can kernel smooth little f of S and you can kernel smooth big F of S. And now you have an estimate of V. And from that estimate of V, you can kernel smooth. What is the problem? Well, this problem N in there often varies from auction to auction. And so even when you have, say, 1,000 auctions, each of which has, you know, between 10 and 20 participants, you've only got 100 pieces of data. And the problem with that is that that's often not enough to do kernel smoothing particularly accurately. And so that's kind of the fly in the ointment. We want to now look at the maximum of something. And why? Because the Dutch auction is going to be sigma of Z, the policy function evaluated at the maximum valuation. So how do you do that? Well, let's do it in general. Consider some X, which denotes the kth order statistic. And what do we know about the kth order statistic? Well, at X. Well, it lies between in an interval X, comma, X plus delta X, and there's N minus K below, K minus 1 above, and 1 in the middle, right? So this first, maybe, is this oh yeah, there we go. Can anyone see that? Anyway, this is the multinomial formula. I'm going to go up here. This is the multinomial formula. This is the N minus K people behind. This is the K minus 1 people ahead. And these are the people in between. And then if you just take the limit of that, what you get is the PDF of the kth order statistic, which you can then summarize like this in terms of an incomplete beta function. And so now that we've done it for any K, we can do it for, say, the largest one, K equal 1. Well, that's its density. And this is K equal 2. That's its density. So why is that interesting? Well, this is F of V. This is the second order statistic, and this is the highest order statistic. Okay, so obviously on average, the highest order statistic has a bigger mean than the second order statistic, which has a bigger mean than the valuation itself. What about if you take a transformation, namely the bid function of the highest valuation? Well, you plug it in here, and then you get this, right? So if you were looking at data, what you should find is that the winning bids at English auctions sometimes go far out into the tail. Whereas at sealed bid auctions or Dutch auctions, they end at S bar. They just stop there. Right? There's nothing beyond that. And what's going to be handy for empirical work is that density is strictly positive at the boundary. And what's more remarkable, I guess, is that the mean of that FW distribution is the same as that FY of W distribution. That's kind of interesting. So that's kind of what auctions puts on the data. And you can now, with a reserve price, figure out, what's the probability of each of the events. No winning price at an English auction. Well, FV to the N. One guy shows up. It's a binomial evaluated at 1, and then when M exceeds 1, it's the second order statistic. So this is what the density or the PMF/PDF of the winning bid at an English auction looks like. So you can see why if you try to if you see kernel estimates that have support everywhere, there's a problem, right? Because it shouldn't happen. There should be point masses. And why is it happening? Well, because there's some either unobserved heterogeneity other than the valuation heterogeneity, or some observed heterogeneity that's not being accounted for. These distributions have very sharp predictions that are almost invariably rejected by the data. Okay, so let's now think through the best environment to collect data. A Vickrey auction. Let's imagine that there is no reserve price. So every one of the NT people bids. And you can see that from the joint distribution of bids, FB, you essentially have the distribution of valuations. And so if you're working from some tech company and they want to learn the distribution of valuations, well, you just use a Vickrey auction, no reserve price, because then at least you'll see the entire scope of the data. And you can kernel estimate it. Now, what happens when you have a reserve price, RT? Well, some of the bidders don't show up, and that's a bit bad, and then some of them do. And how big M is depends on how big RT is. So while you may be able to non-parametrically estimate little f above RT, you're not going to do anything to the left of RT. And so you're going to have to make some sort of assumption in order to get anywhere. My favorite is the Weibull, but you can have yours too. Now, if getting back to this model here, which should have this property, right? What if it doesn't? Well, one way to introduce something is that every auction is terminally unique. There's something about it. Okay, so you get a sample of data that you've collected, you've put all your little heart and soul into it, and despite that, it's imperfect. What form could that imperfection be? Well, it could be that there's an additive component that makes every auction a little different, or I like this one much better. And you're saying, well, can't we have something in between? No, you cannot. If you have heterogeneity that's any other form, you're not going to be able, you're going to have to construct a bid function for every type in the first stage of the problem, and then it's going to enter in nonlinearly, and you're going to be in a heap and help and a mess. So what you can do is to realize that if you have a valuation Vn that is perturbed by an epsilon t, and they're independent of one another, that you can calculate the characteristic function of y as the product of the characteristic functions of v and of epsilon. And you can basically take differences of random pairs, and that will then give you a characteristic function of the difference, which you can then get, which is the square of the valuation. So if you have an estimate of d hat of d, you can get an estimate of CV by just taking the square root of the characteristic function, and then using the Fourier inversion transformation, you can get the distribution of V, and then you can, work on the rest. So the point is that under some circumstances, if you have unobserved heterogeneity, the world is not lost, but it's even in this very simple model, it's a heap and help and worse than it was before. If there's observed, if you're doing, sorry, yes, I'm gonna get here. How do you estimate these models? Well, in the absence of this unobserved heterogeneity for a sample of T, well, you know that you can estimate F of W from the sequence of winning bids, right? That's typically all you get at an English auction. And you know what? There's a known function of B given N that you can then invert to get an estimate of V from an estimate of F of W. So that's not hard. You build this jump function, this EDF, and then you just invert it. So that's fine when there's no reserve price. Similarly here, when you have no reserve price at a first seal bid. So in the simplest of worlds, no unobserved heterogeneity, no observed heterogeneity, no reserve price, no N, you can get everything you want here non-parametrically. And that has obviously been attractive to a lot of folks because of the literature is large. What happens when you have a reserve price? Well, you in both circumstances, you don't get to see anything to the left. And if that's at all important, that's a problem. Fine. So what are you going to do if the part to the left is important? Well, you're going to have to take a position on what the distribution of valuations is. And I've always chosen the Weibel. Why? Because it's in the Weibel, in the construction of the optimal reserve price, a certain regularity condition has to be maintained. The hazard rate has to be monotone. And the Weibel has that restriction embedded in it by the exponent in the distribution. So it's a cheap way of imposing the condition for the reserve price. One of the problems with this Gare-Perrine-Vong estimator based off these pseudo residuals is it doesn't necessarily satisfy that monotone part of the hazard rate. And so then you get a whole bunch of different solutions. And then which one do you choose? I don't know. So if you can calculate these particular things, and then you can build this lovely density, and then you can take the log of it, and then you can maximize it with respect to some parameters. Say, suppose you make some gamma parameter assumptions for the Weibel, and then some assumptions for what the covariates might be, and then you're good to go. And so there's a paper by me from a long time ago, in which I did this for timber in British Columbia. And you can reasonably question about its academic success, but it did make $537 million for the province of British Columbia. So a little bit of economics can go a long way in these problems, particularly in objects that are sold in large volumes. So even if you just make a couple pennies per board foot or per cubic meter, you can go quite large. Okay, so once again, what does this have to do with dynamics? Well, I think if you're going to work in this area, you should start with a model within the IPV that has single unit demand. And if you want to extend it, then you want to extend it in a very particular way. I know there are lots of processes that could have multi-unit demand. I'm going to counsel to use the Poisson process. And the Poisson process is built up from an exponential model. And so maybe if I tell you about the exponential, you'll understand why this property exists in the Poisson counting process. In an exponential model, the hazard rate of some event is constant. So if you've been waiting 10 minutes for somebody to answer your phone, but it's exponentially distributed, you're still going to wait 10 minutes. And then 10 minutes from now, you're going to still wait 10 minutes, right? The hazard rate doesn't change. And so conditional on something not having happened, it's still the same distribution. Well, how do you get accounting Poisson processes? Well, you fix an interval. You fix the interval from the Poisson model instead of having lambda, has lambda times t. Let's let t equal 1. And what the Poisson random variable will tell you is how many failures occurred between the time 0 and the time 1. Well, 0 failures, 1 failure, 2, maybe infinite. You go to 1, once again, between 1 and 2, same distribution. It's unaffected. The number of failures in the first interval 0 to 1 is independent of the number of failures from 1 to 2, from 2 to 3, from 3 to 4, and they're all the same distribution. Well, now let's imagine that someone has one unit at a sequential auction. So what's going to happen? You probably don't want me writing on that. I'm going to go. No, I meant on there. I don't know. Can anyone see over here? I couldn't see what Ariel was doing. He just kept pointing at the board. So imagine, I'm going to just talk about it. Imagine that Fedor has 3 units drawn from an urn, and I have 2. And there are 3 goods for sale. So in principle, he could get all of them, or one of them, and I get 2 of them, and all the combinations. Now, if you think about that step function that I drew for you for a single demand, we both have 2 step functions. The distribution of the highest step for Fedor is f cubed. The first order statistic is f cubed, and my first order statistic is f squared. So we come into the auction, even though there were a symmetric number of draws, or symmetric draws for each of us from the same urn, he's working on the highest of 3, and I'm working from a highest of 2. Now, if it's an English auction, that's not going to affect our bid, right? Because we're just going to let it rise. We're bidding our signals, and we're just going to let it rise. He's probably going to win because the distribution of the highest of 3 is everywhere to the right of the distribution of highest for 2. Now, let's say he wins. that marginal utility drops out. And now we're almost symmetric, right? I win. He's working on the maximum of 2, and I'm working on the just 1 draw. So he's more likely to win. So the most likely outcome is I win 1 and he wins 2. Now imagine though, and so what at every stage of the game, there's this asymmetry being included, right? And what is this? This isn't an asymmetry of information. It's like the urn was from a different draw, the different urns. The symmetric IPV model is one where you always draw with replacement from one urn. Our highest valuations in Fedor's is from a distribution that it stochastically dominates mine. It's everywhere to the right. And so that's a form of asymmetry. And what happens in models of asymmetries is there's a phenomenon known as weakness breeds aggression. So because I know I don't have as high a valuation as Fedor, I'm more aggressive than him. Now that's not going to matter in an English auction because I'm never going to bid past my valuation. But in a Dutch auction or a first price sealed bid auction, you'll get a major difference. And what can happen in those auctions is that the weak type, somebody with a lower type actually wins the auction. So, you know, in a symmetric world, all of these auctions guarantee an efficient allocation. The highest valuation person wins the auction. In a world of asymmetry, the Dutch and the first price sealed bid auctions admit inefficiencies. Persons with lower valuations can win over people with highest valuations. That's not true in the English or the Vickrey auction. There, what you get is efficiency. So what does this all have to do with this Poisson model? Well, imagine that each of us gets a Poisson draw. 5, 3, 7, 9, 0. When the highest valuation drops out, what does that conditional distribution look like? Well, in the Poisson model, because of this memoryless process, if I know that John dropped out with his highest valuation, I still don't know anything about how many draws he has. So I still don't know where he is relative to me. And so what this Poisson process does is it keeps the game of the continuation game symmetric. And that turns out to be really important computationally. And so if you were going to pursue dynamics in a sequential world, the way to imagine multi-unit demand is to do it with a Poisson model. Is that the right model? No, but it's the model that you'll actually get some results out of.
Sorry.
Yes.
What does that Poisson process imply in real world? Computationally, it is very non-formable way, maybe, but how do you define that?
Oh, you don't. It's just a model. Yeah, no. Right. Consider a complicated and really difficult problem that you cannot solve. There exists a simpler problem that you can also not solve and start there. So, you know, this is a simpler version of something you're probably not going to be able to solve. So just have a go at that. Right. I mean, all of these are just prototypes on the path to a better model. They're not, you know, no model is right or is correct, but some of them are better than others. I've now run out of platitudes. Okay, so one of the things about all of what I've talked about today, I should know where I am. Oh, great. One of the things that you might want to do, these models are all about allocation and about efficiency. And in many environments, you want to learn, you want to see how learning occurs. And you can't really get any learning in an IPV model because it's private values. And so Milgram and Weber invented this notion or constructed this model of what's called affiliation. And it's a form of dependence in signals. And in mathematics, if you're trying to look for affiliation, you won't find it because it has a different name. It's called multivariate total positivity of order 2. And there's actually many orders of these. There's a whole book about them by Carlin. And what affiliation does is it's a form of dependence that ensures a single crossing, right? So you don't get multiple equilibria. It's extremely strong, right? That if you were to consider the size of the affiliated set relative to the universe, it would be about this big. It's almost non-existent, right? But it's where you need to go. Okay, so what you're going to do if you want to do dynamic structural econometrics in auction is you're going to choose a format and some pricing rules, and then you're going to go forth. I don't know where we are relative to the break, but
Good, 7 minutes.
okay, well, so I'm going to kind of outline kind of two ways that I've pursued with others, and then John is going to step in and do another one that I've done with him and Sunjin Cho. So the first thing I worked on was with Donald and Robert, and we started in about 1994. And in order for time to be important, or in order for there to be any dynamics, there has to be more than one unit or more than one object. And so economists distinguish between multi-unit and multi-object auctions. Multi-object auctions are very complicated to do because they typically involve an apple and an orange and a pear, whereas a multi-unit auction is 3 apples or 3 oranges, and you can often invoke decreasing marginal utility, and that puts a lot of structure on what you're looking at. And so with Donald and Robert, we looked at an English auction, a particular kind, a Japanese version, open outcry, where there were sequential units of things sold. And what we noticed from the application is we knew who all the bidders were, more or less. I mean, their names were written in Cyrillic, but they were enough different that we could pattern match that there were maybe 20 or 40 of them. And what we would see is at different auctions, there would be different numbers of bidders. So we need to have a way of having different amounts of competition from the same group, as well as different amounts of demand. And the Poisson did that. If you didn't get so the way that model works is you get a draw, M, the number of units you want. If it's 0, you don't show up at the auction. If it's positive, you either got 1 or 2 or 3 or 4 or 5, and you can calculate what the strategy is. This is a particularly attractive environment to work in because for all bidders, it's a control limit policy, right? Because it's a stationary distribution, if they all have the same valuation, they bid the same. There's a symmetric equilibrium. And that symmetric equilibrium gets indexed by how many goods they've won thus far. So if they've won 1, that profile lifts up a bit. And you're thinking, how could that be? Well, that's an interesting property of the model, is that when you have multi-unit demand, instead of getting a martingale, we get something called a super martingale. It goes up over time. Anyway, when you look at the bid function in this auction, it's horrendous. It's impossible to calculate. But what you can do is you can show that the outcomes are efficient. And there exists another mechanism, another auction, the generalized Vickrey auction, which is also efficient. So instead of calculating the data generating process for this auction, what we did was we simulated a Vickrey auction and used the average prices from that as the regression function. And then with that, we were able to reverse engineer estimates of the distribution of valuation. Of course, if you're going to use simulation, what do we know? Well, you're not going to be non-parametric, right? Because in order to simulate on a computer, you have to take a stand on what the CDF is, because otherwise, how are you going to invert it to get the values you're interested in? Right. So you have to be parametric, which in our case is not unreasonable. There's only 37 auctions. So I think I'll just stop here so that we can change slides and then